Welcome to the start of our last chapter. Here we are at section 6.1, analyzing antiderivatives graphically and numerically. So first I just want to touch on the word antiderivative. So far we've been using integral, okay, they're very closely related, but we're going to get into that a little bit more in the next section. So I just wanted to write a few things down. So if we have capital F prime of x, so the derivative of capital F is equal to lowercase f of x, then capital F of x is an antiderivative of lowercase f of x. Okay? So if we're using lowercase letters throughout the next section, we will be referring to those as the derivative even if they don't have the prime symbol. So do be careful and make note of that. Okay, so in example 1, we're given a derivative, so we're given capital F prime is equal to 3x squared minus 4x, and we're given one other point. We're given that capital F of 0 is equal to 4. So we're asked to find capital F of b, for b is equal to 4 different values. All right, so we're going to go ahead and use our fundamental theorem of calculus here. Okay, we're not done with it yet. Let's go ahead and write it down real quick. When we have the integral from a to b of the derivative of a function, it's the same thing as the original function evaluated at the top bound minus the original function evaluated at the lower bound. Okay, so in this case, we were given a derivative, so we'll go ahead and plug that into our integral. So we have the integral of 3x squared minus 4x, cap that off with a dx, okay, is equal to, well, we need some bounds. All right, so we're given f of 0, so we would like to use 0 as one of our bounds. All right, 0. And we need to find b at all of these various values. So we'll use b is equal to 1 as our first upper bound. Okay, so this gives us, by the fundamental theorem, this gives us f of 1 minus f of 0. Okay, we can evaluate the integral on the left-hand side using our calculator like we have been. So we have negative 1 on the left-hand side is equal to capital F of 1, that's the one we don't know about yet, minus f of 0, which is 4, so minus 4. We'll go ahead and add 4 to both sides, and we get that f of 1 is equal to positive 3. Okay? We were asked to find f of b for b being 4 different values. So we just found f of 1. Now we need to find f of 2. So we're going to do the same thing. We have two different options here. Okay, we can either choose to go from 0 up to 2 for b is equal to 2, or we could now go from 1 to 2 because we now know what f of 1 is. Either way, you'll get the same result, but I just wanted to make a note that you do have an option here. We're going to go ahead and stick with 0 to 2. Okay. So the integral of our derivative, so 3x squared minus 4x dx, and this is going to be f of 2 minus f of 0. So the left-hand side is going to come out to be 0, and f of 2 is what we need to find, and f of 0 is again minus 4, so we get f of 2 is equal to 4. All right, now we still need to find f of 2.5 and f of 3. I'm going to go ahead and just write the answers here. So f of 2.5 should be 7.125, and f of 3 should be 13. And I'm going to ask you to take a few minutes and make sure you understand this process and make sure you get these answers, except I wrote the decimal in the wrong place. It's 7.125. There we go. All right. Let's move on to example 2. So here we're asked to find capital G of 3, given capital G of 1 is equal to 20, and lowercase g is equal to natural log of x plus 1. So here, capital G is the antiderivative of lowercase g. All right, so lowercase g is our derivative. It just doesn't have the prime on it. We're now using uppercase versus lowercase, okay? So we can use our fundamental theorem again here. All right, we're given g of 1 and we're asked to find g of 3. And we're given the derivative. So we want to integrate over the derivative, so the natural log of x plus 1 dx. And we want to use bounds that make sense in the context of our problem. We were given g of 1, all right, so 1 would make sense to use as a bound, and we're asked to find g of 3, so we should use 3 as our next bound. Okay, so this is going to be, not f, we're using g, capital G of 3, the upper bound, minus capital G of 1, our lower bound. We can use our calculators again to find that our integral evaluates to be 2.16 is equal to capital G of 3 minus capital G of 1 was given as 20, so minus 20. Go ahead and add 20 to both sides, and we get G of 3 is 22.16. So example 3 is again going to use the fundamental theorem, but here we were actually given what the integral evaluates to, and we were not given the derivative of the function. So we can't use our calculator to figure this one out. All right, but we have the integral from 2 to 6 of our derivative, which is lowercase f of x. And then it must be the evaluation of the original function at the upper bound minus the evaluation of the original function at the lower bound. So this is again by the fundamental theorem. And we can't calculate the integral using our calculator, but that's okay because we were given what it evaluates to. It evaluates to 12. F of 6 is what we're trying to find, and f of 2 was given to us as 7. So we go ahead and add 7 to both sides, and we get that f of 6 is equal to 19. Okay? Moving right along to example 4. Here we're given the graph of a derivative of a function, and we're given that f of 0 is equal to 2. So that's the original function value is equal to 2. And we need to find the original function value at 2 and the original function value at 4. So here we're given the derivative of the function, okay, which remember is the graph of the rate of change. So we've done a problem similar to this in the past. We know that in order to find a next point, well, we have to take the previous point and then add up the total amount of change that happened since then, right? So numerically, we have f of 2 is what we're trying to find. And we know that we need to start at f of 0 because that's what we were given. And then we need to add up the amount of change that happened. We do that using an integral from 0 up to the value that we're looking at, 2, of the derivative, which is given to us as our lowercase f of x. Okay, so f of 0 was given to us as 2 plus this integral. Okay, and we don't have the function of the derivative, but we have the graph. Okay, so we can't just plug the integral into the calculator. Instead, we have to find our total accumulated change by finding the area under the curve by looking at our graph. So we're looking from 0, which is here, up to 2. So we're looking between here. Okay, and so we could go ahead and use our counting boxes technique, which we've used in the past, or we can find the area of the triangle, right? When we have shapes that we already know, we can go ahead and use the formulas that we know, and we're trying to find this area in here. One thing that we notice is it's below the x-axis, so that means it's going to be counted negatively. So really, we're not going to be adding this integral, we're going to be subtracting it from our 2 value. All right, so we have 2 minus the area of this triangle. So the area of the triangle is 1/2 the base times the height. Well, our base is 1, 2, so our base is 2, and our height is also 2. Okay? So 1/2 of 2 times 2, well, that's 1/2 of 4, which is 2. So we get 2 minus 2 equals 0. All right, so capital F of 2 equals 0. Next, we're supposed to find capital F of 4. So capital F of 4 is equal to, similar to our last example, we have 2 different options here. We can start at f of 2 since we already found that number, or we can start again at f of 0 since that's a guaranteed. And if you're doing a multi-part problem, it might be a good idea to use the number that you were given just in case you potentially had an error in the first part of the problem. And so this would minimize your error in this section of the problem, right? So if we start with f of 0, which was what we were given, then we want to calculate the area from 0 up to 4. All right, of the derivative, so lowercase f of x dx. Okay, so f of 0, well, that is 2. And then we need to find this integral from 0 to 4 of f of x dx. Well, that's going to be starting at 0, but going all the way up to 4. So starting at 0 and going up to 4. So we notice we have some negative area and some positive area. Okay, that negative area, I'm not going to go ahead and recalculate, but you could. Okay, so we have 2 plus the area from 0 to 2, right? And then plus the area from 2 to 4. And actually, we should be subtracting the area from 0 to 2, right? Because we're counting it negatively. So this is 2 minus 2, which we already calculated earlier. Okay, plus this integral from 2 to 4 of f of x dx. So now we just need to find this area here, which to me looks to be a quarter of a circle. Okay, so 2 minus 2 is just 0. So now let's go ahead and calculate this integral. I'll just write out that 0. All right, so this integral is going to be a quarter of the area of this circle. And we know the area of a circle is given by pi times r squared. In this case, our radius is the distance from the outer edge to the middle of our circle, or 1/2 of our diameter. So we're going from 2 to 4, which means our radius is 2 squared. All right, radius squared. So we have 2 squared, which is 4, divided by 4, we end up with pi. So f of 4 is equal to pi. All right, moving on to example 5. We're supposed to use the graph below to give the x and y coordinates for each local max and min. And then we're also given that g of 0 is equal to 2. So in this case, we are given the graph of our derivative. Okay, so we're given g prime of x. And we need to find the x and y coordinates for each local max. So let's think back to when we learned about local extrema, okay? And remember, we needed to first look for critical points, right? Critical points. And we learned that critical points are anywhere that the derivative equals 0 or the derivative is undefined, right? So let's see, we are given the graph of the derivative. So it equals 0 anywhere it touches the x-axis. So it equals 0 here, here, and here. Those are the 3 points that the derivative touches the x-axis. Okay, and it's undefined in a few locations, one of which being where we have a sharp point. All right, remember things happen too quickly at sharp points. Things change too fast. So our derivative is undefined at this point, x is equal to 6. So our critical points will be x is equal to 0, 5, 6, and 7. And those are not automatically where we have local extrema, right? We need to check a few different things. We need to check if the derivative changes sign over those points, because that will tell us if we're actually curving or not, right? So let's check at x is equal to 0. So looking at our first point here on the graph, our derivative is negative if it's below the x-axis and positive if it's above the x-axis. So to the left of x is equal to 0, we are negative, and to the right of x is equal to 0, we are positive. So we're negative on the left, positive on the right. So we're negative going to positive, so this gives us a local minimum. So at x is equal to 5, what happens? Well, we are positive on the left and negative on the right. So we do change, and this means we have a local maximum. At x is equal to 6, what happens? Well, we are negative on the left, and we are also negative on the right. So it doesn't matter if we're increasing or decreasing, we're still negative. We're still below the x-axis. So this is not an extrema. Not an extremum. Okay? And x is equal to 7. Similar deal. We are also negative on the left and negative on the right. So we are also not an extremum. Okay? But are we done? The question asked us to find the x and y coordinates for each local max and min. Okay, so we have the x values, but now we need to find the y values. So for our local minimum, we know that x is equal to 0. I'll say x and y. is equal to 0, and we were given g of 0 is equal to 2. That's our y value, the function value at x is equal to 0. So 0 and 2. For our local maximum, well, we found that x is equal to 5, but we were not given our function value at x is equal to 5, so we don't know the y-coordinate. Well, how can we find the y-coordinate? Well, our last few examples helped us find function values using the total accumulated area between the x-axis and the derivative function, right? So, our question mark here, we need to take the integral, well, we need to take x is equal to 0 value, which is g of 0, which is 2, and we need to add that to the integral from 0 up to 5 of our derivative. We are above the x-axis, so we know it's going to be positive. All right, and we're looking between 0 and 5. So if it was a perfectly drawn graph, we'd see this is again an area of a circle, but only half of that circle, right? So this is going to be 2 plus half of the area of this circle. So we have pi times r squared. So our diameter is 5. So half of our diameter is 2.5, and then we need to square that. Okay. So we end up with 2 plus 1/2 of this area, so we get 11.82. So this is our y value. So we just need to go ahead, erase my little question mark, and write 11.82 in our point. Okay? And finally, we have example 6. So given the graph of the derivative, we're supposed to sketch the function and label each local maxima. Assume that f of 0 is equal to -1. All right, so we have a lot to do for this problem. We need to graph the original function based on the graph of the derivative. So the first thing we want to find are our critical points, right? So our critical points are where our derivative is 0. So our derivative is 0 at 2 and at 5. So x is equal to 2 and x is equal to 5. Okay. And we can also decide if these are any kind of local extrema. So on the left-hand side of x is equal to 2, we are negative. And on the right-hand side of x is equal to 2, we are positive. So we do change sign at x is equal to 2, and we go from negative to positive, which means x is equal to 2 is a local min. At x is equal to 5, we go from positive to negative, so x is equal to 5 is a local max. Okay? What else can we find out about our original function based on our derivative? Well, where our derivative is negative, our function is decreasing, right? So, let's see here. F prime of x is negative on, let's see, from 0 up to 2. 2 is where it becomes 0, right? And then it's positive from 2 to 5, so we are positive on 2 to 5. And we are negative again after 5. So we're negative from 5 up to 6, it looks like. Okay, and our graph doesn't show what happens after 6. All right, so this means that f of x is increasing on 2 to 5 and decreasing on 0 to 2 and also 5 to 6. All right, so we found out where our function is increasing. We found out where it's decreasing. We found out we have a local max at x is equal to 2 and a local min at x is equal to 5. Okay. What else can we find out? How about concavity? All right, so we found the critical points. We found the increasing and decreasing. How about concavity? Well, we know that the second derivative tells us about concavity. So we can look at the graph of our first derivative and examine its derivative by looking at tangent lines, right? So over here we have a positive tangent line, and over here we have a negative tangent line. So here we have a horizontal tangent line, which means our second derivative is 0. It looks like about halfway between 3 and 4. So at 3.5, our second derivative is 0. So second derivative, f double prime of x, equals 0 at x is roughly equal to 3.5. Okay. So we were positive on the left, which means we have to be concave up on the left of x is equal to 3.5. And our second derivative is negative on the right, which means we need to be concave down on the right of x is equal to 3.5. So now we need to take all of this information and put it together on the graph of our original function. All right, so I'm going to go ahead and add some dotted lines in here to give us some sections. So we know that we need to look at 0 up to 2. All right. On this section, we have our first derivative is less than 0. So that means we need to be decreasing. So we are decreasing here. From 2 to 5, we need to be increasing. And from 5 to 6, we need to be decreasing again. Okay. Then at 3.5, our concavity needs to switch. That's where we have an inflection point. Okay. So our inflection point at 3.5. So let's see here. I'm going to divide this into 2. We're still increasing on both of here, but now we were concave up on the left-hand side and concave down on the right-hand side. So concave down here, concave up here. Okay, we also know we have a local minimum at x is equal to 2 and a local maximum at x is equal to 5. If we wanted to, we could go ahead and find the exact values, okay, of our x and y coordinates. I'm not going to do that right now. But we're going to go ahead and say, what about our local minimum being down here and our local maximum being up here? Okay. So let's see if we can connect all of these pieces together while drawing a singular continuous function. All right, so we need to be decreasing and concave up on the first part. So we're decreasing and concave up, concave up. We hit x is equal to 2. We're still concave up, but now we are increasing. So now we're increasing and concave up, concave up. We hit 3.5, which is where we need to switch to concave down. We're still increasing, but now we're concave down, concave down. Then we hit our local maximum, and now we're decreasing, but still concave down. Okay? So our function could look something like this. And again, we were given f of 0 is equal to -1, so we could find our y values for both our local max and our local min. I encourage you to practice and see if you can come up with that. All right? So that was our last example for section 6.1. Please email me with any questions and don't forget to take that comprehension quiz.